Good afternoon, everyone. So our first speaker of the afternoon session is Nicolai Meinshausen, who's down on the program that's coming from UC Berkeley, that's actually moved to the university that we mentioned in very hushed tones around here, namely University of Oxford. And he's going to be speaking on stability-based regularisation.
Thanks very much. I'm glad to be here, and I should warn you, I think, at this stage that the talk is mostly about unfinished work. So if you think it's going to be vague and feels unfinished, then that's because it is. And the first part is still okay, but if you don't like the first part, I can assure you the second part is going to be worse. And I don't know if it's such a good idea trying to introduce high-dimensional models in a workshop on high-dimensional data. So it's mostly here for notation. I call the number of predictor variables P, sample size N, and assume the sparsity in the sense that just a few components of the P I have are going to be really relevant. And mostly I'm going to talk about the context where you're trying to really find the important variables if you have a large number of them, or if you've got many interaction terms. But you could think about some other settings which I'm not going to touch here. But I'm going to show some application to graphical modeling at the end. All right, I've got this fancy. And I want to distinguish between prediction and structure estimation, in the sense that in prediction you would be concerned about finding a good value of beta such that x times beta gives you some reasonable forecast for new observations you're going to see. And distinguish that from structure estimation, which is just concerned with finding the important components of the vector of beta, which we've heard about before. And the methods you want to use in that context, of course, the high dimensionality, the first demand you have then is that the method is computational feasible. So you're constrained to a smaller subset of methods you can use. And of course, for the interpretation, you want to have a sparse solution. So you want to select really a few of the variables and find out which are the important variables. And the examples I mentioned here are boosting and lasso, the usual suspects in a way. But I'm going to talk a bit as well about weak orthogonal matching pursuit, which I think is quite interesting in the context I'm going to show you. And of course, the question you might have in a toy example at least is, suppose you have a set S of truly relevant variables. So the set is now the set of those coefficients which have a non-zero regression coefficient. How well can you estimate that set from the data with the method of your choice and given for some shrinkage lambda? The question is, can you make those two sets kind of agree in some sense, so that the probability that you select the right sets converges to 1, for example, if you have a large sample size. And the question is, what kind of conditions do you need for that to happen? So what are the conditions, for example, on the design X and on the triplet N sample size, the S, so how many truly effective variables you have, and P, the total number of variables. And the second point I'm going to talk about as well, but how do you choose essentially in the end the shrinkage lambda in practice? And I put in practice there because I think in theory there's a nice solution, but in practice it's not so obvious what you're going to do. All right, so the two methods I'm going to focus more about is the lasso, which I'm sure most of you know already, and introduced by you in 96. And the nice thing about it is, of course, it's really quite efficient to compute the whole solution path for all values of lambda at the same time. It's got similarities to boosting, and of course you've got the variable selection effect. The second method I want to talk about a bit more is weak orthogonal matching pursuit, which seems a bit more unsophisticated in a way. It's just an algorithmic approach, and in the way that I understand it, it works like this. It's really a lot simpler than it looks like. The basic idea is you start with the empty model, and then you start adding variables one by one, and the one you add is the one which has maximal absolute correlation with the residuals you have at that time. And the weak part means, well, it doesn't have to be exactly the one which has the maximal absolute correlation, but it could be one which has close to maximal correlation. And it seems a bit simpler, but of course, computationally, it's quite fast as well. And here's the first example, which is a gene expression data set. Again, I'm afraid. And it's 158 samples, and what you measure the gene expression for 4,000 something genes of yeast cells which produce some kind of a vitamin. And the goal there is kind of to identify those variables which are responsible in some way for the vitamin expression. And if you look at the lasso path, it looks like this in this case. So you start with the empty model, and you introduce more and more variables as you change the value of lambda. So for a small value of lambda, you're at that, and for a large value, you're here. And the line I'm showing here is the cross-validated solution. So in the sense, well, you've got to pick the value of lambda in the end. The most obvious thing, which most people are going to do, I think, as a first approach is cross-validation. If you select it here, then basically you select all genes which have a non-zero coefficient at this stage. And if you look at the test error prediction, it looks quite nice. So this is the fitted value versus the absolute value. Oh, I think I have a point here. So fitted value versus actual value. And so the question then is, of course, can you trust that solution in some sense? And what you can do is kind of what Peter Hall talked this morning about, is kind of the authority kind of bad scheme. So what you can do is repeat the whole thing for a bootstrap sample. So the original data are here, it's that path. For the bootstrap sample, you're getting that path here, and the cross-validated solution is again this one. And if you compare the solutions you get, then you select 31 genes here, 39 genes there. But if you compare these two, then just 4 genes occur in both sets, which means the authority of the whole selection can't be big. So the selection you have in the first place of the 31 genes can't be really meaningful. If you do the bootstrap sample, for example, you always get a set of about 40 genes again, but it's always a different set again. So you wouldn't trust that set, I guess, very much, or you shouldn't do. And then you can, of course, ask, well, what might cause the failure in this case of the cross-validated lasso solution? And there can be a number of reasons. One could be that conditions on the design are not fulfilled. The second one is that picking lambda via cross-validation might not be such a good idea, and it can be shown that it is not. So I think most of the variation we see here can be attributed to having picked lambda by cross-validation instead of doing something else. But the conditions are kind of important as well, so I'm going to talk a brief while about the conditions you need in the first place, which is work a bit further back. So you can think about, well, what are the conditions you need that the probability of selecting exactly the right set of variables converges to 1 as the sample size increases on way up here. And what you typically get, I don't want to get into too much detail, is that you need a condition that the sparsity times log of the number of variables you have divided by the sample size converges to 0 in some variation thereof. And that condition, of course, it looks quite nice because P can be rather big and you're still okay. But the large number of variables, it forces you at the same time to use a computationally efficient procedure in the first place, and it turns out that most of these run into some other problem, which was called the irrepresentable condition. I had it in some other paper called neighborhood stability, but it's exactly the same thing. And this is a condition you need for that equation to hold in the end, even for a finite sample. I mean, for a finite sample setting, you've got exactly the same. And if you look at weak orthogonal matching pursuit, then at least in the noiseless case, Trop had a result, and he called the condition you need the exact recovery condition. I'm going to compare these two briefly and derive the last one shortly. So the idea is, well, if you're doing orthogonal matching pursuit, then the next variable you are going to select, if you take the weakness parameter alpha equal to 1, which means you select in the next step the variable which has the maximal absolute correlation with the residuals. Then in the first step, the residuals are just the response y. And so the variable you select in the first step, for example, is just this one here. And now you can see, well, is that variable going to be in the set of coefficients which have a non-zero coefficient or not? And if it goes wrong already in the first step, then of course you can't make up for it at a later stage because you've already introduced that variable. So you can say, well, when is the variable going to be in the set in the complement of S, so in the set of noise variables, which you don't want to have? Then it's if that ratio is larger than 1. So that's the infinity norm if you take the matrix X and restrict yourself to all the variables in the set in the complement of S, versus if you do that for all the relevant variables in the set S. And the idea, I mean, it's a bit rough here, but the idea is basically that because the signal you have is living in the space spanned by the variables in the set S. For example, if you're in the noiseless case, then you might as well introduce that term here, which is just the projection into that space, because the signal is living in that space, so it doesn't change anything if you project it. So if you then look at these red terms, you can bound that term from above by taking the supremum, which basically means the term on the right-hand side here is bounded by this guy, which is just the L1 norm of the maximal L1 norm of all the rows of that matrix. Okay, I'm not sure if that was too clear, but I hope somewhat. Is it? Okay. So if you repeat that argument, then Trop showed that the condition you need for consistency is the exact recovery one, which is basically saying, well, you take all the variables k, which are the noise variables which you don't want to have, and regress them onto the set S of relevant variables you have, which is basically just this least squares regression here. And the L1 norm of all those can't be larger than 1. If it's larger than 1, at some point, it's bound to go wrong. And then we could show for the lasso, the condition looks quite similar. So the only thing that is changing for the lasso is that you have the sign pattern of beta here in the beginning. So that can be a lot weaker than the condition you have here, because if the signs are kind of paired in a nice way, then they can cancel each other out. But the basic condition you have is still somewhat of the same nature. All right, and that's kind of a bit boring because you don't expect that condition to hold in practice. And if it doesn't hold, then you can show, well, you select all the relevant variables plus a bit more. but still you would like to get around that condition. So here's an example again. It's kind of the simplest example you can construct. It's a toy example, but I hope it's going to be instructive after all. It's if the correlation matrix kind of okay, wait, you've got three predictor variables. Oops. You've got three predictor variables. I can't handle that mouse. And the first two are the ones you want to have. And the third one is kind of the noise predictor variable. So you say the beta has a 1 and a 1 in the first two places and then a 0. So you want to select variables 1 and 2, but not number 3. But now it turns out the first and the second have a correlation of rho with the third one. And if that correlation is larger than a half, then it means the condition I just showed is violated. And you can see, for example, if rho is larger than a half, then the variable which has the maximal correlation with the response is the third one. So for example, if you do orthogonal matching pursuit, then you'll always select the third variable in the first step even. And so you're always going wrong even in the first step. Okay, and the same for the lasso in this case. And here's a geometric picture of what happens for the lasso, and it's kind of the xy plane here is the plane spanned by the first two variables, and the red dot symbolizes the beta you have. So the beta has non-zero coefficients exactly in that xy plane, has a 0 component in the third dimension. And the gray shaded area here is the L1 loss kind of the lasso. It's an octahedron, and where the blue shape of the L2 loss touches that octahedron, that's going to be the lasso solution. So in that case, it's the blue ball. But if the correlation is a bit larger than it touches here in that surface, so you're going to select a positive part of that third variable, which you don't want to have. It's just a geometric interpretation here. All right, so ways around that include typically two-stage procedures. With two-stage procedures, I mean that typically you want to select the first estimator which comes close to the true pattern you want to have, but it includes a few more variables which you don't want to have, for which the condition I mentioned is violated. So you have an estimator of that form where the L2 loss is going to 0, and then based on that first solution you do a second run, for example, of the lasso, and now you penalize those variables more which have a small coefficient in the first solution. You penalize those less which have a large coefficient in the first solution. And then, for example, Zhu showed that the selection is going to be consistent, at least in finite dimensions. Or you can do hard thresholding as well of the first solution. But the downside of those approaches is kind of you need to pick the lambda, and then you need to pick another shrinkage parameter kind of in the second round, and it's not quite clear how to pick the lambda in the first place, so it's not getting any better if you add more. All right, there are a few more of them. And the question is, well, is there an alternative way of going about selecting the right set S? And here's where the vague part starts. So if you look again at the toy example I just showed, and you just add a few more variables here, but it's essentially exactly the same problem I showed you here before. And you have again that beta 1 is 1, beta 2 is 1, and all the remaining coefficients for all the other variables are exactly 0. So what you want to select is variables 1 and 2, but you don't want to select all the rest. Okay. And if you look at the solution of orthogonal matching pursuit, then what it does, of course, if that value of rho is too high, it selects the third variable in the first step, and then in the second step it selects the first, and then in the third step the second variable. So I show the coefficients as a function of m, and m is the number of the iterations I'm doing, so effectively the number of the variables I have included in the model. And it's clear that it's got to select the third variable in the first step because that has got the maximal correlation with the response, but you don't want to have it in there somehow. So if you now do weak orthogonal matching pursuit, for example, with a weakness of 0.75, then it effectively means in the first step, for example, you look at the maximal correlation you have, and instead of choosing exactly the variable with the maximal correlation, you take the one which is at least within 0.75 of that number. And if you look at, so you can rerun that, and it's a not deterministic algorithm. And if you do it once, for example, you might see exactly the same thing as before. But if you run it a second time, it might happen that in the first step you select the second variable as your first one, and then the first one as the second variable. And the point is, once you have selected the first two variables, there's no need for the third one any longer. So you're not going to select the third one if you have selected 1 and 2 before 3, kind of. And so sometimes it can go wrong. You select the third one. Sometimes it's going okay. And if you look at, so you can make a plot. What is the probability for each variable of being chosen if you select, for example, m variables? So you can have a plot of where you have on the x-axis you have m, so you include one variable, 2, 3, 4, 5, 6. And on the other axis you just plot what is the probability of choosing that variable with weak orthogonal matching pursuit, for example. And now the picture looks a bit different. It means the third variable is either selected in the first step or it's not selected at all. So that curve is kind of flat. And for the first and second variable, you see that the probability of being selected converges to 1 if you include at least, say, 5 or 6 variables. Which means now the situation is different because it's clear that variables 1 and 2 kind of stand out from all the other variables. And it just suggests in a way that you can use that scheme to separate, to make a selection and say this is going to be the set S, the estimated set S, and the rest are the remaining variables which have a low probability of being chosen. They are discarded, which is a bit similar to what Peter Hall said in the beginning this morning, just in a different context. So the idea could be that, well, you put a gray box somewhere here and say, I want each variable which I'm going to select should have a probability of being chosen at least 0.9 or something if I include 15 variables or something of that sort. And all the other variables which don't make it up there, I want to discard them as kind of noise variables. So more formalized kind of, you could say, well, as long as you have a forward selection strategy as you have for orthogonal matching pursuit, then you can say, well, the stable set of the variables is kind of those which have a probability of being chosen above a certain threshold. And the question is, of course, well, how do you choose that one? So in the next plot it's just the same plot again. Here it's up to m equal to 25. Here it's up to 200. So you see, if you shift that gray box, it doesn't matter too much in that entire example. You're always going to select the variables 1 and 2, and you're always going to discard variable 3 and all the other ones. But you've got to pick that box in a way, so you've got to pick the value of pi and q. But what you can do is say, well, there's an intuition behind it in a way, saying you can choose those values in a way such that you exclude clear noise variables from being included in the model in the first place. So the idea is, well, if you're willing to make the assumption that the design is random and the distribution of all predictor variables, or at least of a subset of the predictor variables, is exchangeable, then you can call V the number of those predictor variables you're going to include in the final model. And then you can say, well, the expected number of false selections you're going to have in that way is bounded by that quantity. So for example, if you say Q is the number of variables you should include in the first model, in the first iteration, and that should always be of square root P about. The intuition behind that is a bit that, well, if you take square root P variables for one set of the data and square root P variables for another set of the data, the probability that there's going to be some overlap is quite small. And if you work it out, you can select Q and pi in a way such that you control that expected false positive rate. And so going back to the problem I mentioned with weak orthogonal matching pursuit, you might ask, well, okay, so if you use that scheme, what are the conditions you need to have a consistent variable selection? And the conditions for now are that I need to fix the dimensionality of S and N, so N is the set of the noise variables. Okay, and the design can't be singular, of course. And then that is the technical assumption in a way. I'm just going to say I fill up the predictor variables I have with even more noise predictor variables, which I think is kind of essential, but I don't want to go into too much of a detail. And the third one is, of course, that the minimal non-zero value, it's a standard assumption, can't vanish too fast for n to infinity. But if you remember, the most crucial condition for the success of orthogonal matching pursuit in the first place was that the exact recovery condition is satisfied. So that's the condition you have up here again. And the alpha is included, so if you have a weakness of, say, 0.5, then you need to have that quantity bounded from above by 0.5. Now with the stability selection, what you can do is instead say, I don't need that quantity to be bounded by 1. It can be bounded by any value, so it can be quite large. And if you just assume there's some value of gamma for which that quantity is bounded, then and that value of gamma is larger than 1, then you know that lasso and orthogonal matching pursuit can't select exactly the right set of variables you want to have. But the stability selection I mentioned is going to succeed in that case. So if you have Q of smaller order than square root of P, and the weakness parameter is small enough in some sense, which depends on the gamma, then the stability selection is going to pick exactly the right sets of variables, even though lasso and orthogonal matching pursuit are going to fail in this setting. So it means just looking at the authority, so what's called this morning, how often is the variable going to be selected if I do it under a bootstrap sample, is going to succeed in settings where all the other methods are going to fail. Okay, and now coming to the second point is, in practical situations, often it's quite hard to pick, I think, to pick the right amount of shrinkage. What is usually done is to either take cross-validation, but it can be shown that it doesn't work out well. So the model you will have in the end, if you take cross-validation, is always going to be too large. And the second option you have is take a value which from theory you know works out nicely. The disadvantage with that approach is kind of you need to know the noise level, typically at least, and it's quite hard to say in a practical application what the noise level is, especially, for example, if P is a lot larger than N. So here's an example again. It's again the vitamin expression data. And what I did was I kept 4 genes just as they were and permuted all the other 4,000 and something genes with a random permutation. And what I show in the lasso path is the red path is is the coefficient path of the non-permuted genes, and the black lines correspond to the coefficients of all the permuted variables. Basically, it's saying, well, you definitely don't want to have any of the black variables in there because they can't be meaningful in this context. And you want to have potentially those 4 red genes in there. And if you now look at what happens with cross-validation, then cross-validation picks the line here. So it selects a model with 23 genes, and that model includes 3 of the non-permuted genes, which you want to have, but it includes also 19 of the genes which were permuted, so which are not meaningful. And if you look at the comparing plot in the stability path, so which I mentioned before, then at least 3 of the non-permuted genes stand out quite clearly from all the rest. So in that plot, it would be a lot more obvious what I think, even intuitively, what the right amount of regularization is. And you wouldn't pick variables which just have a probability of being selected of 0.1, say. And with the method I showed you, you can use a pre-specified value of that cutoff. So I would say that it is useful in this context to think about it in this way because you can control the expected number of obviously false variables which are going to be in the model in the end. And at the same time, it turns out that the ranking of the variables you have is quite often a lot better than with the original procedure you had. So for example, here's a simulation example, and it looks a bit confusing, but what it is doing is just it's taking a data matrix X from a real data example and then generate a new response variable Y kind of by creating a vector beta, which has mostly 0 entries, but then you have 3 up to 30 non-zero components of it. And the signal to noise ratio is varied between 1/4 and 4. And P and N vary between 600 to 4,000 and N from 250 to 750. And this is the plot you get if you do that for the X derived from a motive regression example. What happens there is, wrong button. What you have here on the x-axis is the number of wrongly selected variables, and the black dots are kind of the cross-validated solution. So, for example, for one beta setting and one signal-to-noise ratio and one data set, you get that cross-validated solution. So you pick about 30 to 40 wrong variables in there, and you know which are the wrong variables because you designed it in the first place. Not you, I. And then you can look at what is the proportion of the relevant variables you select at the same time. And so that's, for example, for that guy here, it's 0.8. And the corresponding estimate with the stability selection is sitting here. So you still select about 0.7 to 0.8 proportion of all relevant variables, but at the same time the number of wrongly selected variables is down to 0.5. And the value of 0.5 is no accident in this case, because I chose the value of q in the first place to control the number of wrong selections at 0.5. Granted, that control, it needs an assumption which I'm not sure is satisfied in that context. It probably is not, but still it shows you, it gives you the right ballpark of how many false selections you will have in the final model. And if you repeat that for different amounts of sparsity, signal to noise ratio, and so on and so on, you see that you lose a bit in the proportion of the relevant variables, but you reduce the number of wrong selections tremendously. And you can do the same thing for boosting instead of lasso, and the picture is about the same, so there's no real change there. And here's another data set for the vitamin gene expression data. It's another data matrix X. And you see about the same behavior again, except for this one where the performance of stability selection kind of drops a lot. And you see as well here that the value of 0.5, which I demanded in the first place, is a bit conservative. So usually you would have a bit fewer wrong selections, but again, it gives you the right idea of how many false variables are going to be in the final model. The next comparison for those data sets as well, you could say, well, you just pick a different solution on the path, so you just pick a different lambda, but it's actually not quite the case. So going back, you can say, well, what happens if I compare these two while demanding that I make no wrong selection at all? So I demand for both the lasso, for example, and stability selection that I pick the tuning parameter in a way that I don't have any false selection, and see how do they compare. And if you look then at, well, both have no wrong selection at all, but you can compare what is the, oops, sorry, wrong button. What is the number of the correct selections you have, for example, in this case with the lasso, versus the number of correct selections you have with stability selection. And you see it's always, you get at least as many correct selections with stability selection. So it tells you you get a better ranking, at least for these cases, than you get with the original procedure. And the different circles here kind of for various signal to noise ratios, various sparsities, different sample sizes n, and so on. It's always the same picture. And I have to say, in this setting, I did not delete some points which were here below the line, so it worked out quite nicely by itself. And the same for boosting. Well, yeah, you would hope that, right? The same for boosting. It's kind of the same picture here. And for the other data set I mentioned, the same thing happens again. Now let me just briefly give you an application to graphical model selection. So the task here is kind of, you've got about 100 genes again, and you want to infer kind of what is the underlying graph you have. So if you assume it's a multivariate normal distribution, about you want to have the relevant entries in the inverse covariance matrix here. Oh, sorry. I'm going to learn it some stage. So you look at, if you assume the data are about multivariate normal, then you can say what is the inverse covariance matrix, and then you want to look for the important entries in that inverse covariance matrix, which, if you plot it as a graph, give you kind of the edge in the corresponding graphical model. And there are various techniques to sparsify that, so to get really a sparse graph from the data you have. And if you look at the solution you get, for example, with the graphical lasso, which again is your invention, I think, then you get that path for various values of the lambda, so to say. So if you pick a large amount of shrinkage, you get the graph. On the left, if you pick not so much shrinkage, then the graph is going to be quite dense. And now you can say with stability selection, well, what I can do is to repeat that kind of for subsamples of the data and see which of the edges are going to be chosen a large number of times within those subsamples. And then I can say, well, for example, I want to control the number of false edges in there at a certain value, for example 1, and pick the value of the threshold accordingly. And if I do that, then I get the picture in the lower row. So that is the path I showed you before. In the second row, it's kind of the graph you get if you do the stability selection for each of the lambda values in the first row. And the cutoff is always chosen to have the number of false selections bounded by 1 under that exchangeability condition. But what you see in any case is that the solution is hardly changing, so you always get almost the same solution, which I think is quite reassuring in that context, because you don't have to be too concerned about which value of lambda do you take. It doesn't matter, you always get approximately the same answer, no matter which value of the lambda you chose in the beginning. And just as a demonstration of that effect, you can say, well, what happens if I permute all the gene expressions randomly for each gene separately? So I know that there's no correlation at all in the data, and the true graph is going to be the empty graph. There shouldn't be any edge in the graph. And now I've chosen the lambda now. I've chosen the lambda in a different way. I've chosen it again to have, I think here, 100 edges, 200, 300, and so on. So in the second row, it's again what happens if I use that value of lambda and do stability selection. Then I get, in almost all of the cases, I get back the empty graph. I might select an edge here and an edge there, but I said in the beginning the number of false edges in the graph I want to have should be controlled at 1, and that holds exactly in this case. So you can be sure that the number of false edges you're going to see if the true graph is the empty graph is at most 1. These are some conclusions with which I think I'm going to skip to leave more time, and a few references, and thank you very much.
Again, have plenty of time for questions.
It was a very nice talk. I just want to say, first of all, that around the time of the Lasso paper, the paper by Chen, Donahoe, and Saunders.
Oh, yeah.
Had very much the same idea, so we should,
should
definitely be co-credited.
Yeah.
A comment about the question about the first part. In the counterexample that you had, would be another way to deal with it would it be to shrink the covariance matrix of the regressors towards the identity first, which the elastic net does that. So you shrink it first, and then you apply the lasso to the resulting problem. I would think that might do it, because the problem is you had too much correlation of x3 with the other variables, which was sort of contaminating the selection.
But if you shrink it towards the identity, how can you be sure that you pick the right variables in the end? I mean, then I can see you solved that problem, but couldn't you get a problem somewhere else, kind of? I mean,
well, you're leaving the correlation with y the same, but you're shrinking the correlation of the x's towards the identity, so that
which is going towards what Fan said, kind of in the Schroer independence screening. So you just look at the marginal correlations then. But what is going to happen then in the case where, I mean, you could think of cases, I think, where that is going to go wrong, right? If you just look at the marginal correlation of a variable with a response, I think you can show examples where you include variables you don't want to include. But we can talk about maybe that a bit later.
There are many things I missed about your talk, so I'm going to take a meta view.
Well, as I said in the beginning, it's vague anyway, so.
Details. so one way, maybe what you're trying to do, and maybe have done, is that you have some sort of problem, and we first would want to know if we could do a computationally infeasible thing. Look at all 2 to the p
Yeah,
subsets. When is that problem solvable? I mean, I'm just,
yeah,
we're all the experts here. When is that solved? Now, I can't look at all the 2 to the p subsets, which is a deterministic thing. So I've had these deterministic algorithms, the lasso and the, what do you call it, the partial, the
I forget now, math.
Right.
It's math.
There are many things I'm not an expert on in computer science where you have that situation. We can't compute 2 to the p.
Yeah.
The best deterministic algorithm is not too good, but there are a lot of random algorithms we can compute that do quite well with a lot less computation than checking every case.
Yeah.
So in a view, you're doing randomized algorithms. So it's very interesting to know, are there randomized algorithms for these problems when you could solve the problem with 2 to the p? I don't know when you can solve that beat any deterministic algorithm we've been looking at, and if you found one, we're on the way to finding one. That
Yeah, in a way you could view it in that sense, but it wouldn't exclude. Yeah, there might be something in computer science which is done already, and we just don't happen to know about
Yeah,
it.
I'm just saying, you're using probably an algorithm that doesn't have a guarantee to do as well as looking at all 2 to the p. But probably with high probability it does better than your deterministic lasso.
Not uniformly, but
With high probability, yeah. Or I don't know, I mean not uniformly in this parameter space.
Yeah.
Anybody else who knows more about these things?
I mean, I just to ask about that, is it the case in that your first example that if you put in x1, x2 together, you could try all subsets, that you'll see that x1, x2 together has a small error than
you
if
would see that. Yeah.
Yeah, so that would
So,
be an example.
so it really is it's a selection issue. The fact that you put in x3 first is that you're not looking at all subsets.
I mean, I have to confess, I'm not quite sure if it's really been worked out what happens to if you do the complete, if you go through all subsets, what is going to happen in the noisy case. I'm not quite sure if there's a
For
vision.
example, it's clear you would have no problem. You don't know.
In the try example, there wouldn't be a
That's why
problem,
I'm
yeah.
saying it.
So exactly, that's what I said, kind of the large P is quite often not a problem in itself in the theory, but it forces you to use something computationally efficient, so you can't do all subsets. And of course, in the try example, yes, you could.
Some of the problems you describe, in particular some of the problems related to regularization, are really a direct result of large P. For example, that's the sort of thing that forces you onto cross-validation, which
Yeah.
gives you a whole lot of genes or a whole lot of components that are not particularly helpful.
Yeah.
Well, one of the things that we've tried in this case is to use a massive dimension reduction step first. So you start with P, which is very much larger than N. And then by using correlations or just straight linear correlations or something related to that, reduce dimension very quickly from P down to something which is of the same order of N as N. And then that's much more manageable. And assuming you haven't made too many important errors in that step. And that's probably not too bad an assumption if you're using something like linear correlation and your aim is to fit a linear model. Then to work with a smaller number of components and be a bit more clever then because you don't have P, which is very large at all, in order to regularize.
Yeah, this is a bit what I mentioned about the two-stage procedures,
Yeah.
where you do your first round trying to bring down the large number of the variables you have. But I think one problem still persists if you do that, and namely the exact recovery condition, for example, I mentioned, is still going to be there because you're going to include those variables in the pre-filtering, and if you use the same method kind of in the second one as well, so if you don't go to all subsets, for example, then you'll still face exactly the same problem for those variables. So just bringing down the high number of variables p to
Yeah.
a moderate size, I think for that particular problem is not going.
I agree with that. But it is going to help you with the regularization step.
Yeah,
For
sure.
example, choosing the penalty.
Yeah.
You're now in a situation where you can use the adaptive lasso rather than the regular lasso.
Yeah.
For the graphical model, do you need additional constraint like this covariance matrix has to be positive definite? Because you're selecting these things.
No, in this case, no. It just works on the structure of the graph. So I'm not involved if I use that method with the coefficient estimates in any way. I don't even touch them in a way.
That's why I was thinking
So-
that to make it complex.
So what you get is the structure of the graph, and then if you want to have the corresponding estimates of the covariance matrix, you'd have to do that kind of in the second step.
I'm wondering whether there might be a problem with choosing the tuning parameter for your stability selection. I think you called it pi, the probability of being included.
Yeah.
In the situation where you have many variables, several variables that all have about the same relationship with the response. So suppose you have, in one situation, 5 variables that all have the same correlation with y. And in another situation, you have 50 such variables. The probability of being selected for any one particular variable is going to be very different in those two situations. And even if you set that threshold using probability of false detection for noise variables or something like this, it doesn't really solve this.
You're saying because you have weak power to see any
Because in one
to see
case
any
you
of
have a
those
large
sets,
set
because yeah.
from which any variable is equally likely to be selected. So the probability for any individual variable will be small.
Yeah.
In another case, it will be.
If I understand correctly what you're saying, then I fully agree. And in theory, it kind of works out because you can, if you're willing to make an assumption on the sparse eigenvalues, kind of, if you say the sparse eigenvalues of, say, of order, I don't know, the square root of n variables is bounded from below, then you're okay for the theory. But I would agree that in practice, it's mostly going to be an issue of losing power because you might not see any of those. And I think it would be interesting to work that in a more hierarchical fashion. So you can think of a situation where you can say, well, there's a group of variables and I'm sure there's something interesting in that group, but I can't really pin down, is it variable 1, 2, 3, 5 within that group?
I think the way you're doing it now, you may not see any of that group because each one of them will not appear very often because they're all interchangeable.
Yeah, exactly. It would have to be an extension of that method. Mm.
The WOMP selects variables one by one. So for that nice asymptotic result to hold, what's the stopping rule? When do you stop?
That is exactly the value of Q I mentioned. So you can fix Q to be of order square root of P. Just fix. And the interesting thing is if you look at that, it doesn't depend too much on which stopping rule you choose. So you choose the value of Q just as a square root of P half, which is so what I always used, and use the threshold pi to control kind of the number of false projections you have. But if you look at the results, I couldn't show it to you here, but if you look, for example, at some, maybe this one example is instructive here as well. For example, here, that's kind of the same stopping rule involved. It's just a shrinkage parameter you choose instead of a stopping. But it doesn't really matter that much where you're going to stop. As long as you do the stability selection, you end up with almost the same thing in the end. So it's quite insensitive to that chance. But from the theory, it would tell you you should take of order square root of P.
Hello. Is your analysis reliant on the X fixed assumption that the design is sort of fixed, or
No, it doesn't.
okay, you can consider it a sample from a covariance matrix?
Yeah. At least I think there shouldn't be any problem.
Okay, I believe we have a break now, and we reconvene at 3:30.